You know that feeling when you're streaming a movie and right at the absolute climax of the story, the screen just freezes.
Oh, yeah. And you get that little spinning loading wheel.
Yes, exactly. You get the spinning wheel and you're just sitting there completely suspended, waiting for the data to finally catch up.
It's basically the universal symbol of an information traffic jam. I mean, the system simply has too much data to process at once, so it just stalls out trying to organize everything.
Right. Now, I want you to imagine that exact same spinning loading wheel, but happening inside your own brain.
Oh, man. That's a painfully relatable image for a lot of people.
It really is. And it's something every language learner, or, well, really anyone trying to communicate a complex idea, knows intimately. You're in the middle of a conversation, you have this, super nuanced thought you want to express,
Yeah.
but as you open your mouth to deliver it, everything just freezes.
Yeah.
Your brain is essentially buffering.
Yeah, you experience what we call sentence lag. Exactly, sentence lag. And that's what we're going to cure today. Welcome to the deep dive, everyone. Our mission today is to completely fix this buffering issue, especially for English beginners or anyone who struggles with stringing together complex thoughts.
And it is a very real cognitive bottleneck. I think the frustration really comes from the fact that you possess the vocabulary, right? Like you know exactly what you want to convey.
Right. The words are all there.
Exactly. The words are there, but the structural delivery system in your mind just crashes while trying to assemble them in real time.
So traditional language learning usually tries to fix this by handing you this massive, boring textbook full of abstract, disconnected grammar rules.
Which nobody actually enjoys.
Right. Nobody likes that. But we aren't doing that today. The sources we're diving into approach English grammar not as a list of, arbitrary exceptions to memorize, but as a clean, highly organized software system.
It's such a fascinating perspective shift. We're going to explore what linguists call attributor components.
Which sounds incredibly technical. It does, yeah. But it's really just the technical term for the descriptive words we use in sentences, the things we attach to other things.
Right. But we're looking at them entirely through the lens of computer science today.
Specifically, we're looking at a concept called memory mounting. We're examining how your brain mounts or attaches information to a core subject without crashing the whole system.
I am so excited about this paradigm shift. By the end of this deep dive, you are going to understand exactly how to manage your sentence payloads so you can speak with zero latency.
No more buffering wheel.
No more buffering wheel. So to understand how to build a complex sentence, we first have to understand how the foundational pieces of data are loaded into our brains. All right, let's start at the base layer.
Okay, let's do it.
If we're treating an English sentence like a running application on a smartphone, what is our core starting point?
The foundational starting point is always the noun.
The noun.
Right. Think of a noun as the main object you are initializing in your system. It's like opening up a blank user profile on an app or setting up a bare server.
So at that stage, it's really just an empty container. Like if I walk up to you and just say the word server.
I have the core category, but I have absolutely zero metadata.
Right. You don't know what kind of server it is, who owns it, what it's doing, nothing.
Exactly. That complete lack of detail means we have to attach or, mount descriptive properties directly onto that noun.
And this is where it gets really cool, because the subconscious rules our brains use to process English handle this attaching process in totally different physical locations.
Yes, depending entirely on the sheer size of the data we want to add.
Right. So let's look at the first method, which is Tier 1.
Tier 1, preposition stack mounting.
Yes. What happens when we only have a tiny bit of information to add?
When a description is incredibly lightweight, we're talking just a single low overhead word, like the adjectives secure or fast or legacy, the English compiler prefers to load it before the noun.
So we're talking about everyday phrases like a secure server or a clean legacy script.
Correct. And there's a very specific, almost hardware-level reason for this layout in the brain. It creates a really fast cache lookup with minimal system memory overhead.
Wait, unpack that a little bit. Why does putting it first make it faster?
Well, human short-term working memory is notoriously limited. We can only hold a few pieces of unattached information in our heads at any given split second.
Right.
So by putting a single, tiny descriptive word first, your brain creates a fast temporary storage space. It holds on to the concept of secure for just a millisecond.
Oh, I see.
And by the time the listener's brain reaches the noun, the property is already allocated. The core noun server arrives to anchor it instantly.
It's honestly just like the temporary copy-paste clipboard on a computer.
That's a great analogy.
Yeah, like you copy a tiny bit of text, hold it in that fast memory for just a moment, and paste it right on the noun that immediately follows.
Exactly. It's an instant, seamless processing pipeline. O of one fast compilation, if you want to use the computer science term.
Right, totally.
Mm.
And I notice you can even chain a couple of these lightweight words together, right? Like you said earlier, a clean legacy script.
Yeah, that works because clean and legacy are such small data packets. Your short-term memory can juggle them effortlessly until the word script shows up to give them a home.
Okay, I love the clipboard idea for small things. If I have a tiny word, I just slap it in the front-loaded stack. But, and here's my pushback. Let's test the limits of this.
Go for it.
Since this front-loaded stack is so fast and so seamless, why can't we just put all their descriptions there?
Oh.
Like, if I have a massive, complicated description, doesn't this front-loaded stack have a strict physical size limit? Won't I eventually crash the system?
You absolutely will. You will run headfirst into a critical buffer overflow.
A buffer overflow. That sounds serious.
It is, linguistically speaking. That temporary front-loaded clipboard has a very strict capacity limit. If you try to force a massive multi-word block of data into that front slot, the listener's brain simply drops the information.
Because it runs out of holding space before you ever get to the actual noun.
Exactly. It completely loses track of where the subject even starts.
This actually transitions us perfectly into Tier 2, and honestly, the main problem non-native speakers face. Trying to cram too much data into that small front-loaded stack.
Right. It's the #1 cause of that sentence lag we were talking about.
So let's try to break it on purpose. I want you to hear what that crash sounds like in everyday speech.
Okay, lay it on me.
Suppose I want to describe a server, and the detail I need to add is that it operates with high security protocols. If I force all that into the front-loaded clipboard, I get, we need a with high security protocol server.
Oh, wow. Yeah, the listener's brain actively rejects that.
It sounds so completely wrong.
It does, because as they hear with, they open a connection. Then they hear high, then security, then protocols. Their temporary memory is entirely full, but they still don't have the core object.
Right.
By the time you finally say server, they've completely forgotten the beginning of the sentence and have to mentally backtrack to piece it together.
And I see this struggle constantly with language learners.
Mm-hmm.
A beginner might be translating from a native language like Chinese or Japanese
Mm-hmm.
that actually does allow much larger, heavier descriptions to be stacked in front of the noun.
Right. Different languages have different operating system architectures.
Exactly. So they formulate this massive complex thought, and then they try to cram that enormous payload into the tiny English front-loading clipboard.
And they just freeze.
Yeah. It's like trying to pass an entire SQL database file as a single variable name. It just doesn't work.
It doesn't. When the descriptive data gets too heavy, the English system protocol forces a context switch. We move to Tier 2.
Which is post-position heap mounting.
Exactly. Instead of loading the data in front, the payload is routed to the back of the noun.
So we shift from the quick front clipboard to a larger storage box at the rear.
That's the clean architectural fix. In computer systems, when you have large, complex data blocks, you don't keep them in your fast cache. You allocate a larger, more stable memory space on the heap.
Okay, let's walk through the exact diagnostic trace of how the brain compiles this without crashing. We have the phrase, the server with user credentials. How does the mental software handle this?
It executes a very clean 3-step process. Step 1 is instantiating the core noun. You lock in the base memory block by saying the server.
Which solves the memory limit problem right away. I hear the server, and my brain locks that core object into long-term safety. I don't have to juggle anything.
Exactly. Then step 2 is opening a reference link. We use a pointer token.
A pointer token like the word with.
Yes. With acts as a pointer trigger. It signals to the listener's brain, hey, keep this connection open. A heavy metadata payload is about to attach to the server.
It's like a warning sign not to close the thought yet.
Right. And then we arrive at step 3, which is resolving the heap metadata.
The payload mount.
You load the complex data block, in this case user credentials, into the rear slot. And because of the pointer token, it binds all those properties directly back to the server we established in step 1.
I love how logical this is. Step 1, instantiate core noun, the server. Step 2, Open reference link with. Step 3, resolve payload, user credentials.
It flows perfectly.
Another classic example is Professor of Linguistics. If a language learner tried to force that into the front clipboard, they'd say, the corner of linguistics professor.
Which, again, causes a system crash. The front slot just cannot handle the pointer token of.
But by declaring the asset first professor, throwing a pointer of, and mounting the payload at the rear linguistics, it's totally stable.
It remains perfectly stable.
Visualizing it this way is so helpful. It makes traditional grammar mistakes seem less like, failures of intelligence and more like simple file management errors.
That is exactly what they are.
Like imagine someone pausing, stuttering, buffering, and then saying, the containing 500 lines of code script is broken.
Right, they're trying to shove an entire textbook of information into that tier 1 front slot.
It creates an immediate error. But the debugged version is so effortless. Declare the core item first, throw a pointer, mount the payload at the rear. The script containing 500 lines of code is broken. Boom.
Boom, the buffering wheel disappears.
The speaker can pace themselves because the heavy lifting is safely stored behind the noun.
Shifting those static heavy phrases to the back keeps the whole sentence from toppling over.
Okay, so that handles static descriptions like big boxes of information. But what happens when the description isn't just a static phrase?
Now we're scaling up.
Yeah, what if the description is doing something? Like how does the English compiler handle a fully active running process attached to a noun?
This moves us into the ultimate scale, the highest tier of noun modification, which is tier 3.
Tier 3, virtual subsystems.
Yes. In traditional grammar, you'd hear this called attributive clauses or relative clauses.
Which, again, sounds incredibly dry. Let's stick to our software model. What is a virtual subsystem?
Well, sometimes a simple static phrase like, with user credentials, just isn't powerful enough. You need to describe a noun using an active timeline with verbs and objects.
Okay.
When this happens, the system literally spins up a fully containerized virtual machine directly inside the modifier slot.
Wait, really? A virtual machine running inside the main sentence?
Exactly. This mini sentence has its own subject-verb actors, its own targets, but its entire life cycle is dedicated to modifying one single noun.
Let's break down an example from the sources. The firewall that blocked the cyber attack is offline.
Okay, great example. Let's trace the data pipeline.
Right.
We start exactly the same way we did in Tier 2. You establish the core node first.
The firewall.
Core node locked in.
Then you have the subroutine. Block the cyber attack. Right, which is a complete miniature data pipeline on its own. It has an active verb, blocked, and a target object, the cyber attack.
Exactly. It's a running process. But the challenge is, how does the system connect that running process back to the firewall without everything getting jumbled?
We need a network bridge.
Yes. The network bridge is the word that, or sometimes which or who. This word logs into the main sentence, grabs the reference to the firewall, and passes it directly into the subroutine.
Oh, wow. So when I say that, it effectively says to the system, take the core noun and run it through this specific action sequence.
You've got it. To the listener's brain, this entire active virtual machine scales down seamlessly into one unified description. The firewall that blocked the cyber attack is offline.
That is it's such an aha moment.
It really is.
Once you see modifiers as scalable memory slots, you realize that whether you use a single word, a phrase, or an entire active clause, you aren't memorizing different arbitrary grammar exceptions.
No, not at all. You are just running different tiers of the exact same mounting protocol.
It's the same protocol. You're just selecting the right slot for the size of your data.
Exactly.
Let's actually summarize this master memory mounting matrix for you listening so you can really take this and use it to cure your sentence lag.
Perfect. So it breaks down into 3 manageable sizes. First, you have Tier 1, the stack cache.
Right, the front-loaded clipboard.
This is for single, lightweight words like adjectives placed before the noun because the brain can instantly process them like a secure server.
Small file, front slot, super easy. Then we have Tier 2, the heap reference.
Right. This is for your heavier descriptive phrases. Because they're heavy, you shift them to the back of the noun and use a pointer token, like a preposition.
So the server with user credentials, declare the asset, throw a pointer, mount the payload.
Exactly. And finally, Tier 3, virtual subsystems.
The mini apps.
Yes. This handles full clauses where actions are occurring. The location remains at the back of the noun, but you use a network bridge like that, or which, to feed the noun into the action.
The firewall that blocked the cyber attack.
You got it. Tier 1, Tier 2, Tier 3. It's a completely predictable, Hardware layout.
I think the core value here, for anyone listening, especially if you're an English beginner trying to build fluency, is that when you stop memorizing abstract rules and start viewing sentences as logical components mounting to functional slots, your speech becomes completely stable.
It really does. The panic just disappears. You just have to keep your references clean and manage your payload distribution wisely.
If it's a huge thought, don't shove it in the front clipboard.
Right. Drop the core nouns safely into the conversation first, keep the connection open, and just hand over your heavier details at a comfortable pace. Error-free communication.
It totally debugs the whole buffering problem. But, looking at language this way, it leaves me with one final kind of provocative thought to mull over.
Oh, what's that?
Well, if achieving fluency in a language is really just about viewing it as a predictable hardware layout and compiling it on the fly, what other messy, chaotic areas of human communication could be instantly solved if we just treated them like software algorithms waiting to be debugged?
That is an interesting question. If we can map something as organic as syntax to system architecture, the potential for debugging how we argue or debate or even negotiate is pretty huge.
Right. Maybe all of our miscommunications are just buffer overflows waiting for the right pointer token. Keep your core subjects stable, manage your payloads wisely, and we'll see you on the next deep dive.